Thank you, everyone. Good morning. It is still just morning. I think we have 5 minutes to go till it's not morning. So today, I'm going to try and focus on, there's a lot of things we're going to cover here. It's like how we got here, where in-memory computing's going, and kind of why it's going in that direction. And the theme of everything is kind of convergence. We're seeing a lot of convergence, not just in memory computing itself, but in the kind of solutions that it provides and the types of things that we are working with and the benefits we're providing to like a number of, well, almost all industries. And technologies are also converging. So if you think about enterprise computing, cloud, IoT, they're not islands. They're not treated as individual things. You have to think of them as a connected ecosystem. And this is true of almost all of the technologies that people are involved in today. You have to think about how do all the pieces work together. And that also includes how do you integrate new technologies like AI, machine learning, into various different types of applications. Where does it fit? How does it work? And you might think, is AI in-memory technology? Well, you're doing the processing in memory typically, but also it's very, very important to be able to do real-time scoring and utilize AI in real time, and that's really where it comes into play in memory architectures. Every industry is undergoing this digital transformation. There's not one industry we've spoken to that isn't trying to move towards the future, and what is legacy is rapidly speeding up, right? It used to be that something you had crunching data away in a basement somewhere that's been sitting there for 30 years was thought of as legacy. Some customers are talking to us today about technology they put in 5 years ago as legacy. So this digital transformation is the process by which you try and automate and move things towards the future. And in-memory technology plays a hugely important part in that. And some of the drivers behind this is just data. Now, this is from IDC. They released this a few months ago. And lots of different people have different numbers for data. But if you believe this, then they're saying 16 zettabytes of data are generated annually. And that's 16 with 21 zeros. If I put that number on here across the entire screen, it's a lot of zeros. By 2025, they're estimating that's going to leap to 160 zettabytes of data. Now, anyone with a math background will see this is a nice exponential curve. And what that means is that every 2 years, we generate more data than has ever been generated in the whole history of mankind before that. Every 2 years. Now, this is the interesting bit for in-memory computing. Right now, we're dealing with about 5% of the data is generated and needs to be dealt with in real time. By 2025, they're estimating that 25% of that data, so 40 zettabytes of data, will be generated and need to be dealt with in real time. And 95% of that will come from IoT. Now, what IoT is a totally different story, but it's basically anything connected to anything that can generate data. And the real kicker here, I don't know whether you can read the small print at the bottom, this study was sponsored by Seagate, a storage manufacturer. Not enough storage is being generated to store all of this data. In fact, nowhere near enough storage is being generated to store all this data. So estimates are between like 3 and 10% of data that's generated could ever be stored. There's literally not enough hard drives, flash drives, magnetic tape, newfangled 3D crystal technology on the planet to store all the data that's being generated. So if you can't store all the data, what can you do with it? And your only option really is that you're processing that data in memory before it ever hits disk, and you're doing that in a streaming fashion. It's just a logical conclusion. And this is partly what's driving in-memory technologies. It's not just IoT that's generating huge amounts of data. We've got customers in security, and they're generating 12 terabytes of data a day just from security data, and they haven't finished connecting up their sources yet. Right? You can't possibly store all of that data permanently, but you need to analyze it to make sense of it. So part of the questions are, how do you avoid losing or ignoring valuable data while you only store what you need to store? And some of that is information science. Some of that is, how do you extract the information content from the data? There's a difference between data and information. How do you correlate events, again, in memory, for immediate insights and proactive responses? So how do you react quickly to the data while also deciding what you're going to store? And there's a big difference here. If you're, for example, getting 1,000 events a second from a turbine, and it's telling you, I'm spinning at 10,000 RPM, right? In a second, you've got 1,000 data points, but you probably only got one piece of information. It was spinning at 10,000 RPM for the last second. But if something happens, if it drops down to 5,000 RPM in a millisecond, you need to react instantly in that millisecond. So there's two things you're doing here. One is you are not storing all the data, you're filtering it, you're aggregating it, you're turning it into information in memory, but you're also able to react instantly anything happens with really low latency. And both of those things require in-memory technologies. And how do you do all this to better serve your customers? On a security side, protect your reputation, and beat competitors. So all of these are business concerns that can be helped by in-memory technologies. And real-time use cases cover all industries. And you're not expected to read all of this. The point of this slide is to show you that there's a lot of different use cases in a lot of different industries that can be benefited by doing real-time in-memory types of applications. The real thing behind all of this is that all data is generated because something happened. Data is not generated in batches. Files aren't created in batches, they're written line by line. Databases aren't created in batches, they're written row by row, right? But for some reason, we were doing processing in batches. And part of the reason for that is because in-memory technologies were seen as niche. They required a lot of memory, they required a lot of CPUs, they were expensive, and you couldn't process all data in real time. That was only for people that needed to do it, like people trying to do instant stock trading or prevent their nuclear reactor from exploding. Those are kind of the two extremes, but that was really what in-memory technologies were for, because it was seen to be expensive and difficult. But that's no longer the case. Storage was cheap, that's why things were done in batch. But you don't need to do that anymore, because memory is getting cheaper, CPUs are getting cheaper, and it's possible to have really, really big memory machines and CPU machines that don't break the bank, that can perform really, really well. And so you can treat the data now as it needs to be treated. Your databases can be turned into data streams, your files can be turned into data streams. Things that are streaming, like devices, can be turned into data streams, well, they're already data streams. Message queues are already data streams, right? So all of these things can now be done in a streaming architecture, and so stream processing is this major infrastructure requirement. And if you're doing stream processing, you're doing continuous data collection, you're doing in-memory processing, in-memory analytics, continuous storage of information, and you're trying to extract the value immediately while also being able to store the things that you want, that all requires an in-memory computing platform. Now Gartner, and the blurb for this talked about Gartner. Gartner has a whole taxonomy for in-memory computing technologies. And they break it down into different sections. So they talk about the hardware, a memory-intensive computing platform. That's the RAM, SSD, multi-core, all those things, the high-speed networking, even things like deep learning units that allow you to do kind of real-time machine learning, GPUs. All of this becomes the underlying substructure. Then you have the in-memory databases, and you have the in-memory data grids, two currently separated technologies in the Gartner taxonomy. you have a high-speed message infrastructure. How do you move stuff around really quickly and do that in a scalable, persistent, reliable way? And then you have the applications on top of that for things like in-memory analytics, stream processing platforms, and other things that you might do with in-memory data. And the other thing is kind of their catch-all. So they can say that we cover everything. So these different pieces are used in different ways in different types of architectures. And I think there's a presentation going on right now. It's talking about HTAP, which is the hybrid transactional analytics processing. And this is where, quite simply, you have the database and the analytics coexisting in the same memory space, so you can do really high-speed analytics on transactions that are happening within a database, right? So that incorporates quite a number of the in-memory components that Gartner talked about. You have their hybrid integration platform, which is a pretty nebulous thing right now, but it incorporates a whole bunch of different technologies, and we think it's most likely going to include real-time processing, stream processing as part of that integration, which would include the high-speed message infrastructure, stream processing platforms, and the in-memory data grids. Right? So those are kind of the two Gartner things. And you notice the word hybrid being used a lot here, right? And hybrid basically just means you're converging, you're joining things together that didn't used to be together in order to make a whole. And that happened maybe a couple of years ago with stream processing or stream analytics, where things like complex event processing was its own category. It was its own software market. And now no one talks about complex event processing anymore as a standalone technology. It has been subsumed into streaming analytics. So STRIIM as a company, we focus on streaming integration analytics, which is kind of a cross between those two. And so we have a stream processing platform, high-speed message infrastructure, in-memory data grids, right? So that's all part of our platform. Then, of course, also in-memory analytics and visual data discovery, and that's all kind of part of this category, which is streaming integration analytics. And that's also covered by Gartner in different ways. It's covered by Forrester in different ways, and the various analysts talk about that as well. So these are all different ways of piecing together all of the bits, right? And if you think about kind of how this works from a in-memory architecture perspective, you need your high-speed message infrastructure, you need a distributed in-memory data grid, and that's really important for stream processing because if you're going to join things together, you're going to join context information that you've loaded into a grid from databases with streaming data. You need to do that in the same memory space in a really high-speed way, otherwise you slow down your data streams, right? So that in-memory data grid is important. Some way of storing information, doing data collection, data delivery, in-memory analytics, they're all kind of really important aspects of how do you build this kind of stream processing platform. And now you have choices here, right? You can say, do I do this in an open source way? Do I try and build this myself from all the bits and pieces of open source? Do I do it in a proprietary way? Do I use something that is totally handcrafted by some vendor? Maybe it's written in C++ or something else. It doesn't use any kind of open source pieces, and it's harder to integrate with open pieces, but is very specific in what it does and meets certain criteria. Or do I go this hybrid, there's that word again, open core way, which is utilizing the benefits of open source with some proprietary special source on top of it to actually get you to the end result quickly. So you think about building it from open source. Now, there's a whole process that you have to go through here. It's not trivial, right? For every piece of that infrastructure, I just added a sample on here of the available open source technologies, but there's probably a lot more for each one of these things, right? So you have to go through and you have to say, okay, this is what I want to achieve. I need to look at the bits of open source that are available and work out how they can all work together to give me my end result. And if you look at that from a development process perspective, that's not the end, right? The end of that would be, well, I also have to add an API or abstraction layer so it makes it easier for the next set of developers to build stuff, and all this glue code that makes kind of clustering, scalability, reliability, security, management, all of those kind of enterprise grade things kind of work across the whole stack that you're using. And the process is, pretty long-winded. I'll step through it very quickly. First of all, you design it. We just designed it. We had a architecture diagram. Right? You probably do it in a bit more detail than that. Then for each one of these components, you have to identify what are your choices and evaluate each one. Right? You could just trust someone and say, okay, we're going to use Kafka because everyone else is using it. But is that the best choice for your particular goals, for the things that you really want to achieve, right? The same with Spark. Is that the right choice for what you want to achieve? Can you live with a micro-batch architecture? Do you need a true real-time architecture? Do you need to look at the other choices that are available? So you evaluate each one of these things. And then you need to integrate them together. And when you're integrating them, you may have to re-identify something because some of the things you've chosen don't work with the other things. Or they might use a different programming language. You may have issues integrating that way. There's lots of things that can go wrong in that integration step. Then you obviously are going to test it, which could mean you have to do some rework, etc. And then you have to maintain it. And there's lots of things that can happen with open source that are really bad, right? Anyone here use Kafka or know someone that's used Kafka? Anyone feel really burnt when the APIs change between 0.8 and 0.9 and 0.9 and 10 and 10 and 11? That's a big problem, right? Because that means that you're having to upgrade because of new features or security bugs, security patches, etc. But now you have to redo everything because the APIs have changed, right? So that can be a problem. The other thing is that the open source can be deprecated. We're working with a customer. They spent a year working with some open source components to try and build some security monitoring application. And then this was vendor supported open source. And the vendor said, oh, we're not going to use that anymore. We're not going to contribute to it. We're end-of-lifing it. You have to move to this completely different thing that has completely different APIs. So that wasn't a good feeling, right? So deprecating means you have to go through that re-identification process again. And then, of course, you need to get support on it. And only once you've done all that can you start building your applications, right? So it's a pretty involved process. Now, if you look at the other choices here, proprietary, obviously, you just get the proprietary thing and you build it. But it might not be able to integrate with everything you need. It might not meet all your requirements. This hybrid open core model is getting a lot of traction, and it basically means that it's a vendor that's providing it. They've taken pieces of open source, like in-memory data grid or message queue, and they're adding value to that in some proprietary way. And that could be by adding enterprise-grade functionality, adding additional layers, maybe putting a UI on top that makes it easier to work with. These are kind of the hybrid open core types of things. And anyone interested, we have a white paper on our website written by Tony Bayer of Ovum talking about the real costs and benefits of open source software. It's a very interesting read. So if you're doing that with hybrid, you just install a hybrid and then you're kind of building your applications. So that's kind of the difference. The people building the hybrid have gone through the process of joining all those bits together, doing all the evaluation, making the right choices so you can start building the applications quickly. And then you have to think about enterprise grade. And enterprise grade for in-memory computing, I think I had a whole session on that last year here. So I won't dwell on everything, but you have to focus on scalability, reliability, security, and integration. Now, things like security are really hard if you're building stuff from open source because all the open source pieces have their own different security models or no security at all. And you have to try and put some layer in that maybe gives you role-based security or other authentication and authorization mechanisms to actually use the bits as you go up the stack. And you might think, well, we don't have to worry about it because everything's in memory, no one's going to hack it. You have to think, until 0.8 or until 0.9 of Kafka and in-memory message bus, there was no security, which meant anyone could just connect to any message bus and just read anything that was on it, right? Which isn't a good thing, right? And so when you're trying to build a solution for an enterprise, you have to think about all these things. So scalability is basically how does the in-memory computing platform as a whole scale? How does it scale for volume of ingestion? How does the memory scale so that you can load stuff into memory, maybe in the memory data grid. How does your processing scale? There you worry about how many cores you need, how are those cores distributed across a cluster, etc. And how do you scale in any data you're persisting? Reliability is also important, right? Enterprise customers typically want some guarantees. In memory is volatile, it's in memory, right? If you lose machines, you lose the memory. So how do you ensure exactly one's processing and guaranteed results in memory architecture? These are things that you have to think about, especially if you're trying to build it yourself, and you have to test that and ensure that that works across a whole bunch of different scenarios. So this is something to definitely bear in mind when you're building or looking at in-memory computing technologies. Security, I mentioned, isn't just kind of the authentication and authorization process. It's also encryption, doing that maybe even in memory if you're worried about people hacking the memory itself. But definitely over the wire, you need to encrypt things. And this can be very granular. I mean, you can have an analytics application that is working against various data streams. Some of them might have publicly identifiable information, secure information you need to protect in it. But the end results might not be, right? So you can give people access to the end results of all this processing, but no one should have access to the raw data streams that maybe contain credit card information or social security numbers. So how do you do all of that locking down of things and do that across all the layers? And don't think just because it's running in your networks that it's safe. Right? It's definitely not safe. People can hack through VPNs, they can steal security credentials, and once they're in a network, so anyone in your network has to be treated as a potential threat as well as anyone outside. And integration is also really important. You have an in-memory computing platform. How does it integrate with all the stuff that's outside of it, right? How does it collect data? How does it deliver data? How does it integrate with things like machine learning? How does it integrate with other in-memory components that may be not part of the platform? So these are also things you have to consider of an in-memory computing platform. So just taking a look as an example at our architecture, what we did, we have integration with lots of bits of open source because that's important because our enterprise customers are using open source. And then we also use open source as part of our platform. So if you look at all the pieces that we have our own high-speed message infrastructure that is almost network speed, right? And that's built on top of the Java version of 0MQ and uses cryo for serialization. It's really, really fast, but it's in memory. Right? So if you lose a machine, you lose the memory, you lose whatever is in that queue. And you can mitigate that somewhat. We have kind of a checkpointing mechanism that keeps track of what's being processed and allows you to rewind, etc. But if the sources of data are things that aren't rewindable, so you can't go back in time and recover from a point in time, and things like files and database logs and things like that are rewindable. But things like devices, if they're sending you data all the time, you can't ask them, hey, devices, send me the last half an hour's worth of data again. Firstly, because they probably don't have it, and secondly, because you probably can't even ask them that question. So that's where a distributed persistent high-speed message infrastructure like Kafka would come into play, because that can sit right at the source, and that can collect all of the data, and then you can rewind into that. So that's kind of an important thing. It's kind of this hybrid between in-memory computing and persistent storage that is really, really useful. But something like Kafka should not be used at every point of your processing data flow because you're going to slow things down. Anywhere you're doing I/O, you're slowing things down, right? So you need this combination of a in-memory only messaging and persistent messaging for reliability, failover, and also for kind of application decoupling. Then you need to integrate a in-memory data grid for loading reference data and joining that with streaming data. You need some distributed result storage. We chose Elastic as our default, but you can kind of plug in other things there. And then you put in all this glue code, right? So you have the scalability pieces, you have reliability and exactly one's processing, you have role-based security and encryption, you have management and monitoring, right? You have APIs for interfacing with the platform and working with that. Then you have things like data collection, data delivery, and in-memory processing of data. So how do you do the filtering, transformation, enrichment of streaming data? How do you do complex event processing, pattern matching, correlation, anomaly detection, all of these things, right? So that's all part of how you build kind of the platform. Now, the thing you'll never get with open source is, these two pieces, right? Even if you're an enterprise and you're building things from open source, you're not going to spend the time and effort to build a UI that allows people to build applications, right? You're not going to go through the effort of building a dashboard builder that allows people to build dashboards. You're just going to code the applications and create bespoke dashboards, or utilize something that is a dashboard framework that allows you to build dashboards, but you're not going to have this capability to empower end users to work with the data. And that is really important because we're talking about in-memory computing technologies, but the end goal is enabling people to work with data and to get value out of data and get value out of data in real time. And so that needs to be empowered by giving them capabilities through UIs and other means. And we added in a command line as well for people that like scripting languages and VI and things like that. But the UI is really essential if you're talking to business customers, to business analysts, to data scientists that want to work with the data directly. And some of the proprietary IP that we had to add over the top of what was available in open source, I won't go through all of this, but it includes adding in change data capture so that we can get real-time streaming, inserts, updates, and deletes from databases. So turn a database into a data stream. Being able to do this kind of scalable stream processing and have the same partitioning logic for streaming and data caches. Adding exactly once processing across not just simple data flows, but complex data flows that might involve in-memory data windows, cascading windows, event pattern matching buffers, and all these other things that can kind of get in the way of being able to recover and do exactly once processing. And then, of course, security and encryption, etc. So what are we seeing in-memory computing being used for? And I'm just going to go through a few things that we're seeing at customers. And the reason for this is just to give you an idea of the varying uses that in-memory computing can have. It's not this niche thing anymore. It's being used for so many different things, right? The simplest types of functionality our customers are doing are kind of these hybrid cloud integrations, right? Where they're doing change data capture from a source database, and they're delivering that to a target cloud database to keep that database synchronized. And the end result is that you have a copy of your target database in the cloud, or source database in the cloud, that is continually updated. And the data never lands on disk between the initial capture and the delivery to the target database. All of that processing is streaming, all of it is in memory. So it's not the old school kind of batch processing that you would see with ETL tools. This is true in-memory use of technology to do this kind of real-time cloud integrations and cloud migrations. You can get more complex than that. We see customers that will source from a single source, and then they're targeting multiple things. So they might deliver some of the data into Hadoop, some of it into Kafka, some of it into a cloud storage or cloud database in a single data flow. They're doing all of the processing on that through, we use SQL to define the processing. So they're basically doing processing, they may be doing enrichment of the data. With change data capture, that's really important because if you have a nice normalized source database with, you say you have an order detail table, it might have a customer ID, order ID, item ID, quantity, etc. If you just push that somewhere, maybe onto Kafka or into Hadoop or whatever, all those IDs are meaningless unless you join it with something. So if you load all of your reference information about customers and items into memory, then you can add much more context to that streaming data and allow you to do better analytics and make better decisions. So that enrichment is really important. Then we have more complex scenarios. Customers are using us for cybersecurity. And so in cybersecurity scenarios, you are collecting huge amounts of real-time data. I mentioned 12 terabytes a day and kind of growing. And they're correlating that in memory in real time to spot threats that cross multiple different security devices, right? So if you, as a security analyst, had to deal with every single alert that you see, you'd just be swamped. You just would not be able to look at them all in detail. Every single network router alert, every single VPN alert, firewall alert, everything, right? It's way too much data. But if you can correlate all of that and say, I'm going to put in some rules that if for the same IP address I see this many alerts here, an alert here, these alerts here, and maybe something happening in the endpoint security or antivirus, then you have a much better picture, and you can treat that as a high priority alert that you have to deal with straight away. Oh, and by the way, all the data is already pre-correlated, so you can see everything immediately. Right? So that gives you these instant insights, and you're now proactive rather than reactive, and you're not doing forensics anymore. You're actually working operationally on real-time security data. And if you're interested in cybersecurity, then my friend Farhat over there, he's going to be doing a presentation at 1:45 today talking about the Fujitsu hardware architecture, their in-memory computing architecture with the Spark M12 servers that allows you to have this scale-up, high memory, high CPU that is really suited for processing kind of large amounts of data and edge computing, etc. And he'll mention STRIIM in that presentation as well, because that's the software they're using to actually do this kind of correlation. So I would recommend attending that presentation. He's a really good speaker as well. Other use cases, we have real-time production quality monitoring, where you're doing IoT, collecting IoT data. You're making predictions based on what you're seeing, and you can predict ahead of time whether the production quality looks like it's going to be bad, and so stop a production line before it, stop an item on a production line before it makes it all the way, and you're not then spending money and resources on things that you know are going to be low quality. And that's where kind of integrating machine learning into the whole process and using machine learning to make predictions in memory in real time kind of makes a great deal of sense. And a similar thing with healthcare monitoring, where you can collect healthcare data and join that with patient information. One customer we had, they obfuscated that data before pushing it to the cloud, so they can collect lots of information in the cloud in an anonymized fashion to do machine learning on, so they can then look for symptoms that you wouldn't see ordinarily. And that gives you kind of the real-time insights into patients, which is really crucial. And you can, if you think about how much self-reporting we do, if you have Apple Watch or Fitbit, and you also use MyFitnessPal, and you're logging what you're eating and all this kind of stuff, if you can join all that data together and make correlations, you can predict if someone just ate a meal and their heart rate has gone down, their glucose levels have gone up, they may need a doctor. And so that kind of information is really important. And then things like location tracking. Again, location is something that you have to deal with in real time. How many of you drive? How many of you use Waze? So Waze is really useful, right? You're driving, it tells you there's an accident up ahead, and it reroutes you in real time, and you get around it, and you get to your destination faster. The equivalent in kind of the enterprise would be, instead of doing that, you get an email after you've gotten home telling you that there was an accident 3 hours ago. I mean, that's the difference between kind of real-time processing and existing batch processing that is still endemic in a lot of enterprises. And so locations are important for in-memory computing because they change very quickly. People move around, things move around. And so we have an example with a partner that built this for an airport where they're tracking passengers and staff, and they're making sure that if there's a hotspot with too many passengers and there's not enough staff to deal with them, that they can automatically route more staff to actually cope with the sudden influx of people. And it's not just people. Interesting correlation between airports and hospitals, and it's wheelchairs. Wheelchairs are essential for both airports and hospitals. If you don't have wheelchairs, you can't get certain people onto a plane or take them off a plane, and so the planes can be delayed. If a hospital doesn't have wheelchairs, they can't get patients in and out of the hospital because they have requirements that people have to sit in a wheelchair. And because as an orderly or someone, you need to be able to present a wheelchair really quickly, what was happening is people would actually stash wheelchairs. They would like find some cupboard somewhere or a sign they could hide a wheelchair behind so that they knew where it was, so that if they were asked for it, they could bring it really quickly. The problem is they go off shift and then no one can find the wheelchair. And that happens in hospitals, it happens in airports. So putting real-time tracking on important equipment and being able to spot where it is can really help with operations of places like airports and hospitals. So if you got any key takeaways from this, it's that theme of convergence, that in-memory computing is converging. You have Gartner talking about HTAP and HIP, and you have streaming integration and analytics, all using different subsets of in-memory computing components, but future in-memory technologies will merge all of these things together to provide you everything you need, right? Everything that you need from in-memory computing perspective. And it's the right time to start thinking about getting all of your data into memory. So doing that requires a streaming first architecture where you are at least collecting all of your data in real time and pushing that into in-memory data streams. You might just like throw that out into Hadoop for now, right? Or push it into a database or into the cloud for now. But that's always just a temporary step. And we have customers that say to us, well, we want to push all of our data onto Kafka. Just ask them why. Right? Kafka is not an end goal, right? Kafka is a message bus. Why do you want to put all your data onto Kafka? Oh, well, because we want an enterprise data bus with all of our data on it. Yeah, but why? What are you going to do with it? Oh, we're going to run some analytics. Okay, now you're talking. Yeah, we want real-time analytics. We want to update multiple target data stores in real time to keep them always updated. You know, those are the reasons that you need to look for. And so the starting of all of that is this real-time data collection where you need to at least collect data in real time and push that into in-memory data streams. And also to be able to do this pre-processing of data to turn it into information before you store it. And you do need to think about kind of end-to-end platforms that pull together multiple pieces of in-memory computing into a single architecture that enables you to do things in an enterprise-grade fashion that you can expand your uses of in-memory computing across different enterprise requirements and different applications, and look at open core platforms, hybrid platforms that embrace open source, integrate with open source, but maybe add in all the enterprise-grade stuff and proprietary content for value add, right? So just a little bit about us. I'm not going to dwell on us. I tried to make this as educational as possible. We are a complete end-to-end platform. We do streaming integration analytics, and we have use cases across enterprise cloud and IoT. Our architecture allows you to deploy data flows across on-premise, edge processing, and the cloud, so you can have a data flow that spans all of those with data moving between. We do continuous data collection. We have change data capture for databases. We can read files in real time and stream data out as they're written to files. We work with message queues, sensors, etc. You can do in-memory stream processing through a SQL-based language, so you don't need to have developers involved to code to actually build out these data flows. So filtering, transformation, aggregation, enrichment, all through SQL. Also stream analytics with correlation, complex event processing, statistical analytics, all through SQL. Yeah, we enable you to integrate with machine learning to do real-time scoring, inference, predictions, and enable you to trigger alerts, email, SMS, or trigger external systems, and build dashboards and visualizations on top of all of this, with continuous data delivery to enterprise and cloud targets. We integrate with almost everything you have. Just ask us. If we don't integrate with it, then we can. And we are enterprise grade, so we are inherently clustered, distributed, scalable, reliable, and secure. This is an eye chart. You don't need to look at this in detail. It just shows we integrate with a lot of stuff. We work with the big three big data providers, MapR, Hortonworks, Cloudera, the big three cloud providers, Amazon, Azure, Google Cloud Platform. We can read data from all the major enterprise databases, a lot of different connectors on the source side, the target side, and on the integration side. This is what data flows look like in our platform. You can drag and drop these things, do all the processing through SQL, start with sources at the top, go through some processing, write stuff out. It's really easy to use. If you like scripting, we have a scripting language. Looks like a combination of DDL and SQL, and a command line as well, if you like that. And we have a dashboard builder, drag and drop visualizations into dashboard, visualize in-memory streaming data instantly that you can then give this to end users. So this, again, is very easy to use. Nothing in this is hard-coded. This dashboard was built using the dashboard builder. If there's 4 things to remember about us, we are an end-to-end platform that is easy to use. We integrate with almost everything you can possibly think of, and we are enterprise grade. So with that, I'll say thank you. If anyone has any questions, I think we have a couple of minutes. 10 minutes? Oh, that's awesome. Question back here. Correlating 2 streams? Correlating streams is a really interesting thing. If you think about a data stream, if it's running at like 100,000 events per second, and you try and join 2 of those together, correlate them, it's like trying to hit 2 proton beams together in a nuclear collider. Right? The events are really small, they're moving really fast, the chances of them hitting are really slim. So what you typically do is you put the data streams into windows, and then you join the windows together. So you basically say, okay, I'm going to put everything into a 1-second window from both data streams, and then if you join the windows, then the queries that are running and processing that, they will get triggered when anything changes in the window. So whenever a new event comes in from either side in that 1 second. So then if you're joining against those windows, then you're effectively saying, if I see something on this stream, was there something else on that other stream within a second? And you can make the time constraints more concrete than that. You can join on different fields on the data streams. But that's typically the way that it's done. And we have lots of customers that are correlating multiple data streams together. It's a crucial aspect, especially on the security application we have. That correlation, if you think about how do you determine whether the same IP address was used to go across the firewall as was doing a port scan on this network router, as infected these other machines and downloaded some virus software, you're probably correlating that on IP address or on IP address tracked through network address translation table changes as it moves around subnets. So you're doing lots of different correlations, and you're having to do all of that in real time in memory. So the security example is a good one of that, where you are doing all these different correlations to try and deduce what is actually happening. You could also do correlations in pattern matching, and that usually is a little bit more complicated because you're saying, I'm looking for a sequence of events over time that match something. I'm not just looking to join 2 things together, I'm looking to join things together if they meet certain criteria. Right? So if I'm getting sensor information from temperature sensor, flow sensor, pressure sensor, a whole bunch of other things, right? It might not mean anything if the temperature goes up. But if the temperature goes up and the pressure goes up and the flow slows down all within a second, it might mean that you have a blockage in the pipe somewhere and things are about to explode. So that pattern matching, I'm looking for that particular sequence, this going up, this going up, this going down, all within a certain amount of time, is something you can do with complex event processing or pattern matching. Does that answer your question? Do we have any more questions? Okay, great. I'm going to give you an extra 5 minutes then. Wonderful. Been a great audience.